Okay, honors physics students. So we've already introduced the concept of resistance, the idea that as the protons are moving through the circuit, they're bumping into each other, they're bumping to the sides of the wire, and all this limits the flow. They can't just flow as quickly or as easily as they want to. There's some sort of limit inside the circuit. So often we put an object in the circuit that offers this resistance. And so now we introduce the concept of the resistor. The resistor is the thing you put in the circuit that has the resistance. So we want to make sure we're using our vocabulary correctly. Resistor is the object, resistance is what it has. But what's a better definition for resistor? That would be this. It's any device that transforms electric potential energy into some other type of often useful energy. Sometimes it's not useful, sometimes it is, but usually put the resistor in the circuit to do something. And you're familiar with all sorts of resistors in your life. I'm not going to list a whole bunch of them here, but in class I would ask you for a list of them, and after we get going, usually you can generate a very good list. And of course, the first example is the light bulb. And that very basic circuit that you built with the battery, paperclip, and light bulb, or that you saw me build, the light bulb itself is the resistor. So that's the prime example of the resistor. It's the one we most often refer to. But all these objects here, a light bulb, a speaker, a microwave oven, a television, a fan, a cell phone, those are all resistors. Notice all of them use electricity. Electricity, right? That's the flow of charge. It comes from a source of voltage. That means that there must be some electric potential energy. So basically, these are all objects that either you plug into a wall or use a battery for, because you're using electric potential energy and transforming it into something else. Inside the light bulb, transforming into light. And also heat, right? That is also always a byproduct. When the light's been on for a while, you touch it, oh, it's very hot. So that's why I say sometimes often useful, but sometimes it's not, because the light bulb heats up, which is not a really useful form of energy, but is transforming electric potential energy into something else. The speaker transforms potential energy into sound, microwave oven into microwave radiation, the television into light and sound, the fan into the motion of the blades. So all these just are something that use electricity. That's a resistor. Okay? And so now we're going to take some data for a resistor to figure out what its relationship is to all the other quantities that we've been doing here. And so here you're going to be looking at the data chart for the lab report that you've downloaded. We'll be doing a single resistor, and what I'm going to do now is I'm going to shift over to do a side-by-side screen with this and our PhET simulation. Okay, so this is the website you'll be using later on in the activity from the group known as PhET, P-H-E-T, and I've built a simulated circuit. Here is our 5.5 volt battery. Here I've got a meter to measure the current, and here is a resistor. There's a 5 ohm resistor. If I click this, I can show the current. You can actually follow the charges flowing around here. There's a conventional current circuit, so we're watching the positive charges come out of the positive terminal of the battery, go through, and then the resistor here is going to be doing something. What's it actually doing? Well, a lot of resistors actually generate heat, so let's just pretend it's giving off heat as the charges flow through it. I'm also going to take a voltmeter from over here. I'll attach one side to one side to the other, and it's going to measure the voltage drop, as we call it, across the resistor. Okay, so over on our data chart, we're going to first fill in the amount of the resistance, which in this case is 5.0 ohms. Okay, and then what we're going to do is we're going to try to adjust the amount of voltage here so we can get these amounts of voltage, and then we're going to read the currents, and we're just going to fill in our data chart as we go. It's a little bit weird how I do this, but actually I'm going to adjust the wire resistivity to try to get the voltage across the resistor to be the values we want. So let's make this as close to 5 as I can get. See if I can get better. So, all right, so 4.92, so it's not exact, right? So you do want to adjust this to 4.9. We read this as 0.98, so let's go ahead and fill that in. Okay, and now I'm going to adjust the battery voltage down here a little bit, and then adjust the wire resistivity until I get about 4 volts across the resistor. So I've got 4.05, that's pretty close, and we have 0.81, so we can go ahead and fill that in. And again, I'll adjust the battery voltage a little bit, and adjust the wire resistivity until I get 3 volts across the resistor. All right, 2.99, that's really close. We have a 0.60. All right, so again, adjust the battery voltage. Now we're going to try to get 2 volts across the resistor. All right, 2.03, I'd say that's close enough. There we got 0.41 amps. Okay, I wonder if you're starting to see a pattern developing here. See if you can take a guess when I get it to 1 volt across the resistor, what this is going to be. Write down your thoughts. See what you can think it might be. Let's adjust this until I get 1 volt across the resistor. Alright, 1.01, I said it's pretty close. Did you guess 0.2? Yeah? Alright. Hopefully you're seeing the patterns emerging here. So that's what we recorded here. 0.2 amps. Looking good. And 0, 0 would be basically if I were to just break the connection here. Let's do this. And now, obviously, there's no charges flowing, and there's 0 voltage. So you can go ahead and put 0, 0 here as the current when there's no voltage. Excellent. Because I did say the resistor does something useful, and here we can't exactly tell what's happening. Here I'm just going to break this open a little bit. I'm going to replace this resistor with a light bulb, just so we can see the effects of that. So let's put a light bulb here into our circuit, like so. The charge is flowing around. I can put the voltmeter across here if we'd like to. And here, we're just going to change the voltage. All right. So if I have a larger and larger voltage, what's happening to the light bulb? Well, of course, we're getting more and more current here. But what's happening to the light bulb? You can should see it's getting brighter. More and more voltage across it, and it gets to be a brighter and brighter light, giving off more and more energy per time. Right. That should make sense. The battery is a source of voltage, which is energy per charge. If all these charges flowing through, each one has more and more energy. It's got to deposit it somewhere, but that's the job of the resistor. The job of the resistor is transformed into some sort of useful energy. The more energy per charge, the more energy is given off by the resistor. So in this case, for a light bulb, it would be a brighter light bulb. Okay, let's get this back to full screen. So what should we do with this data? What do we usually do with data? Oh, we plot it out, right? So you don't have to get out the graph paper. For this, just in your notes, go ahead and sketch the axes. We'll plot the voltage on the vertical, the current on the horizontal, and, set a quick scale if you'd like to. Obviously, you can use the lines on the paper for the vertical scale. We're just going 0 to 5, make it nice and easy. For this one, it should be really easy as well. And then plot it out, although honestly, even just by looking at it, you should probably be able to figure out what shape it is. But just go ahead and pause the video, do it on your own. Okay, it's real simple. It obviously should be linear with a positive slope. It goes to 0, 0. It's obviously a linear situation here, a linear relationship. Okay, hey, we got a straight line. What should we do? We should find the slope, right? So find the slope should not be difficult. Even without graph paper, you should be able to figure it out. All right, so the slope here is clearly going to be 5 volts per amp. We're just taking delta V over I. This is in volts, this is in amps, so the units are volts per amp. And we got 5, right? It's clearly a ratio of 5 to 1, 5 to 1, 5 to 1, or at least really, really close to it. Yeah. Hey, what else was 5? Oh yes, the resistance was 5, and so here we see the relationship that the slope here represents resistance, where resistance is this ratio of voltage over current. Here, this tells us the units, the definition of the unit for the ohm. 1 ohm is defined as 1 volt per amp. This is actually the definition for the ohm. And here's our equation relating all the terms, although traditionally we rearrange this. This was first discovered by Mr. Ohm, so he gets the unit name after him, but it is also Ohm's law, and we usually solve for delta V equals IR. I'm not sure if it's a historical reason, although honestly this is the way I've always seen it written, so it's the way I want you to see it written as well. I guess it also sort of highlights the linearity of this relationship, right? This is on the Y, this is on the X, excuse me, current's on the X, and the resistance is the slope, so it looks like Y equals MX plus V. But anyway, this is how I want you to box it in our notes, delta V equals IR. Alright, one last thing about this, that not all relationships look like this. Not all resistors will give a linear relationship. Ones that do are called ohmic. And so in that simulation, that was an ohmic device, an ohmic resistor, because it had a constant resistance. In this case, we got a constant slope for the data. Not all devices are ohmic. In fact, a lot of resistors are non-ohmic. They don't have a constant resistance. The simulation, though, you can set it to have a constant resistance, and in class, if we had been doing the actual experiment, we use some really good resistors to have a constant resistance. But that also highlights the fact that I showed you a simulation. I don't want you to just look at a simulation and say, oh, that's how it actually is, so I will give you a YouTube video to watch of an actual experiment being done with a resistor, and you'll see that we get a very similar result, that you get real data, and you still get a nice linear pattern, and we can verify Ohm's law, delta V equals IR, because just looking at a simulation, I don't feel is really enough. You need to see real data that you normally we do together in class, but here you'll watch someone do an experiment.